The first section, I'll just provide an overview. The session is JAX inference in vLLM. And for those of you who know vLLM, you probably know, well, there's no JAX in vLLM. Well, surprise, we're adding JAX to vLLM, and we're really excited about it. So I'll be going over an overview of the types of features that, or how we're designing in like a primarily PyTorch repo using nifty new framework tools called Torchax. This is primarily going to be used for TPU initially. We believe that JAX is a great way to get the best performance on TPU, but we still need the flexibility that PyTorch provides or Torchax provides. And so Han will be going over that in detail. And then I'm going to finish on a new exciting project that we're working on called LLM-d, which is a Kubernetes native high-performance inference stack that takes all the best components from open source, puts it together, and provides great production-grade performance with the vLLM as being the engine, the backbone, the engine backbone. Okay, so first I'll start off with what vLLM is. So for those of you who don't know, vLLM originally originated at UC Berkeley in partnership with the open source community in 2023. So Wizit Kwan, who's one of the founders of vLLM, actually worked at Google DeepMind in 2023. And as a 20% project while he was an intern, he decided to add the TPU backend. And so in 2024, at about the midway point, we had a TPU backend in vLLM, which was really cool. Google, we thought this was awesome, and we really rallied around Wizit while he was at Google. And now TPUs are performant in vLLM. So we're really excited about this. The thing is that today, if you look at vLLM, it only supports PyTorch models. And this is great, but if you look at the majority of TPU usage today, it's actually JAX usage, JAX users that use TPUs. And so we really, really want to support our JAX users. And so we're adding a JAX backend or JAX native backend in vLLM. We want to support 4 paths. So I'm going to spend a bit of time on this slide. So just like I'm level setting expectations. We want to support 4 models. So today in vLLM, we have this branch that's supported. And so if you're familiar with it, you have Hugging Face model checkpoint integration. Super easy, kind of you put your model ID and it just kind of loads up and you're ready to go really quickly. There's also something called out of tree custom model support, which is a plugin where you can bring a custom model, your own model implementation written in PyTorch. You don't have to even create a fork of vLLM. You can just like plug and play, ready to go with this out of tree model registry API. The cool thing about the TPU backend today is because it uses PyTorch XLA. And so day 0 support is possible. And so we can leverage what a GPU user somewhere in the world went and implemented in vLLM. We can actually use that model implementation natively with TPU for the most part. And so Qwen 3, for instance, the new MOE models, those just worked day 0 without us writing a single line of code. And so that's a huge achievement, and we're really proud of that. But as I mentioned, this is just PyTorch models. And that's only half of the story. And in fact, it's not at all close to the whole story with TPU. And so we have this whole other segment here that we want to support in JAX, where you can bring, so say, for instance, Qwen 3 PyTorch trained model, a PyTorch model implementation. But what if a JAX user wants to bring an open source JAX model that's written in JAX or Flax? How would they go about doing that today? I think if I were to, and maybe this is wrong, but if I were to quantify or qualify a JAX user versus a PyTorch user, for the most part, JAX users don't want things necessarily totally plug and play. They like going in and writing like their own custom components or whatnot. And so this provides you with that flexibility. So we're adding a JAX backend to vLLM because, and we're rewriting certain components so that they run really, really well on TPU. And this isn't necessarily like a JAX or PyTorch XLA thing. This is really just because GPUs are fundamentally different from TPU, and some logic just doesn't really mesh as well. And so as you move from here to here, you get great performance on TPU, right? Custom fork 2, a lot of JAX users want to write their custom components, and so they'll rewrite that. The problem is that to support JAX, if we were to do this really naively, we would just have 2 pipelines, like 2 code paths, basically, that are doing duplicative things. And that's super inefficient. We wouldn't be able to keep up with open source if we were to design things that way. And so Pengchong will be covering the overview of how we plan to design this hybridized stack with JAX and with Torchax. For Han, what he'll cover after. But that's like really the exciting part about this talk, what we're really trying to get across. And so how do we support these 4 distinct paths with 1 code path that works amazingly well on TPU? So you'll get a JAX native backend in the second half of this year. You'll have a highly optimized model implementation for TPU. So that means like a DeepSeek R1 model implementation that runs really well on TPU. You'll have max text out of tree vLLM recipes, so that we know that it's really cumbersome to bring like a max text trained model to a serving engine. So that we'll have for you by the end of this year. And then of course, we'll still support day 0 PyTorch. We'll still provide day 0 PyTorch model support with Torchax. And the reason for that, because, sorry, I'm gonna go back. The way we could have done this is we could have just like completely scrapped this, right? And only focused on this because that's the most performant. But we wouldn't really be meeting the criteria of having model support on day 0, which we know is really important for evaluating model quality. So when users first start using a model, they're really just interested in understanding, is this model even suitable for my use case? They're just evaluating quality. They're not evaluating performance. So there's this buffer of time between the time a SOTA model is released and folks have to actually evaluate the quality and to see, okay, well, now that I've actually evaluated the quality and I've assessed that it's suitable, now I actually want to use it in production. And so that gives us some buffer, right? And so Torchax works really well for day 0 support for the most part. I think we're trying to increase coverage so for out of the box. But the idea is that how do you design a stack that can actually gradually be written more and more in JAX to get the best performance possible? So by the end of this talk, you'll understand how that will work. I'll then come back and I'll talk about LLM-d after Pengchong and Han have actually talked about this hybridized stack. Because there's this really nifty thing, I don't know if you've heard of it, LLM-d. It was just announced back at around the same time of I/O. And it's basically a Kubernetes native production stack that will support. So if we just focus on the server, as you know, serving these very complex applications with large language models require additional orchestration tooling to handle things like smart routing, KV cache offloading, hierarchical KV cache, and then scaling disaggregated serving nodes, in a disaggregated way. So you'll also hear about that. So I'm going to hand it over to Pengchong, who's going to go over the JAX deep dive.
So before I review the eventual design that we have, let me walk you through the current design of vLLM and remind you how the things work. So in the core implementation of vLLM, it is an engine core class. And inside this engine core, there are 2 important components. One is the executor, one is the scheduler. Here, scheduler is responsible to drive the execution of each model inference step. So for example, at each scheduling step, vLLM scheduler can call whether this is a preview step or whether this is a decode step. And even more, it can mix the preview and decode in one step and run the inference. So here, scheduling is planned at one of the important aspect is scheduling is planned at each model inference tab. So that's what I mean, like, when the scheduler happened, it's a very fine-grained scheduling, which it can mix the preview and decode together. So you can see that, the current scheduling strategy can mix a preview and decode in each request. And this is implemented by the chunk preview inference. And also to notice that, each request is not guaranteed to be complete after each scheduling. It can swap in and out. and can be complete in various steps. And if we look at the actual system aspect of the executor implementation, you'll notice that there are one important concept called worker, where worker is a unit to run on one single thread. So in the current vLLM design, because it can run on multiple GPU and multiple nodes, each node will be handled by one single worker. And under one worker class, there will be a model runner, which is basically a model forward wrapper. And model runner will call model forward to run one single inference step. So in this design, you can see that worker and runner actually doesn't do too much intelligent batching and scheduling. All they do is basically listen to the scheduler output from the scheduler and try to run one single forward step. So in this case, executor is only responsible for running the inference in distributed setup. Now, how can we make use of the existing vLLM design and make it work for TPU and using JAX backend? So we introduce a new JAX backend in vLLM TPU, which we follow the same design principle as vLLM. So we reuse the existing scheduler in vLLM design, and we will use the output from the existing scheduler and feed it to the new JAX TPU worker. And this new JAX TPU worker will consume the scheduler output as it does for a vLLM GPU. And underlying this worker will support model execution on TPU. The way that we do that is by leveraging the JAX SPMD design, where we only have one single worker and single model runner, which manage the execution on multi-node, and this is how it works. And in addition to that, the new JAX TPU backend will provide you a collection of highly optimized JAX model implementation. In this collection, we implement various highly optimized model building primitives that new researcher and model developer can leverage in order to build a new customer model. This building primitive includes, for example, the highly performance racked page attention that optimize your attention computation. We also have the customized implementation for key components in LLM, such as sliding window, other feed-forward primitives, and so on and so forth. So that's the first goodies you can get from this collection of model implementation. The second part is through this model implementation, we also show you that the best practice of how to build a JAX model that can run performant on TPU for inference. This best practice includes, for example, how to do the efficient sharding with the JAX mesh implementation, how to do the different parallelism, including tensor parallelism, pipeline parallelism, and so on and so forth. So from there, you can get the example implementation that you can use to implement your own JAX model that can run performance on TPU as well. Finally, our objective for providing this collection of highly optimized JAX model implementation is to cover as many popular open source model as possible, so that you can use those open source model out of box for your various workload. And as I said, that this collection of models also give you the reference implementation that you can use to build your future open source or customized JAX model. Now, I just covered how the new TPU backend can support the public open source model, and also the user journey for you to build your own JAX customized model through this out-of-tree implementation. But there's also another customer user journey that we want to cover, which is for those existing PyTorch model or your customized PyTorch model, how we can leverage the optimization and the goodies that we built from the from the JAX backend to enable you run performance inference on TPU. So here we also provide important user journey for them, for you to kind of leverage the existing JAX TPU worker, but also make you seamlessly use your existing PyTorch model. The key here is that if you have an existing PyTorch model implementation, we have this magic called Torchax, which kind of converts the existing PyTorch model through this TorchAX tool to a JAX class. And this JAX class can then run with this TPU worker that we optimized. And with this user journey, you can use this method to get the rapid support of your PyTorch model. And I think Han will talk about the PyTorch TorchAX magic in the following. So Han.
Thanks, Pengchong. So this is Han. I work on the PyTorch XLA team, part of CoreML. And I'm going to talk a little bit about how Torchax achieves this JAX and PyTorch interoperability. So when we talk about interoperability, there's actually 3 levels of interop that we can talk about. So the first one is the Python level. Because both PyTorch and JAX happens to be libraries in Python, and it's actually very natural for engineers to import a lot of libraries and then use them together, right? That's a natural thing to do in any language. So as a plain Python libraries, they're of course composable and interoperable as long as you convert the inputs to the right type, right? So you can of course copy the torch tensor into a JAX array, call the JAX function, and then once you have JAX array returned from JAX function, you convert back to torch tensor. Then you have this Python level of interop, which I would argue any 2 Python libraries have this level, so there's nothing interesting there. And of course, the downside of doing this is you do a data copy every time, and we don't want to do that. So the next level of interoperability is tensor level, right? So suppose if torch tensor and JAX array uses the same underlying memory representation, then you can do the interop without copying the data. So for example, if you do DLPack on CUDA, so torch tensor on CUDA and JAX array on CUDA, you will be able to convert them without copying the main data. Of course, you still have to copy the metadata, so there's still a little bit of overhead. So that's nice, but there's still issues, and the main issue is the graph break. So if you do JAX-JIT, the moment you do DLPack inside of a function with JAX-JIT, you will give you an error saying you are concretizing the array. You're reading the value of your array, and that's not allowed where you're JITting because you actually don't have the value there. If you do torch compile, the graph will also break, but torch compile is a more kind of like softer graph break. You will fall back to Python, do the Python thing, and then go back to compile mode. You will do a graph break behind the scenes without telling you. So the best or the ultimate level of interop that we're trying to seek out is actually this graph level, meaning no graph break. You JAX-JIT or you do whatever compile that we do, and then the math from torch ops and the math from JAX ops are all in the same graph. And this is what we're trying to do. Here, the imports are from the old name, which Torchax used to be called Torchax 82. But besides that, this code works today. And here, what we're trying to do is A and B are 2 JAX arrays. F2 is a function that takes the JAX arrays as input and returns a JAX array as output. So for those type of functions, I'll call those JAX functions. I'm very explicit on using jmp.add, jmp.subtract instead of a plus b because there's a operator overload in Python. I just want to be explicit that A and B has to be JAX arrays in order for this function to not throw exceptions, right? And what is interesting, this function is that in the middle, you will call this call torch magic to F1, which is a torch function. A torch function is one that takes torch tensors as input. and returns torch functions, torch tensors as output. And then in the inside of f1, which is a torch function, we again call a JAX function using this call JAX magic, and the function in question is jmp.add. And we can print the result of this, which is this number, and the type is a JAX array. So if you just look at this example now, we actually don't know whether call JAX and call torch primitives are graph level interop, tensor level interop, or Python level interop. However, we can also print out the graph, right? So if we do JAX-JIT and low run as text, we can print out the stable HLO bytecode for the this function. And as we can see, the entire math is inlined as a single straight line graph. So here, this sign comes actually from this sign here. Where is the sign? This sign here, total sign. And then total sign is have a multiplication afterwards. So sign and then do type conversion and multiply, right? So every math operators, both from PyTorch and JAX, is converted into this stable HLO graph in the end. So you get a single straight line graph. And what is nice about this graph is from JAX's perspective. So if you can, as I'm doing JAX.JIT on this function, you can also do JAX.vmap. You can also do, pass it to higher level functions such as JAX.grad, for I loop, scan, all of those functional level transformations. In the perspective of those functions, they could not distinguish this JAX function from another JAX function, which is written by a developer by hand. Right. So how do we accomplish this graph level interop? So these are the rough pieces. So first we have Torchax tensor. This is a Python subclass of torch.tensor. Implements all the methods of torch tensor. So from the list call perspective, it's a value substitution. And then inside of that subclass, we actually hold a JAX array. So the data for this torch tensor is actually backed by a JAX array. And after that, we need to implement the PyTorch ops. In PyTorch, the ops are called A10 ops. That's the name that PyTorch people call their ops. And so we implement all the core A10 ops in JAX. There's roughly 200-ish of them. And then PyTorch guarantees that the other ops, which are around 2,000 of them, decomposes eventually into the set of core A10 ops. In practice, not all of decompose those cleanly, but as we find more, we usually open issues to PyTorch team and they fix it, or we upstream a decomposition. But right now, the coverage is pretty good on the decomposition. So the final piece is a dispatcher hook where we capture what is the current PyTorch op, which is running, and then we substitute that with our JAX implementation. And then JAX-JIT also works. So quick example how this implementation look like. So here is the torch op, index copy, and here is the implementation in JAX. Here is another op, torch op A10 add mm, which is addition plus matrix maximal, and the formula is here. We just write the formula using JAX. And this operator will just put those two functions inside of our registry, where the key is the PyTorch op, and the value is the JAX function, which implements the same semantics, except all their inputs are JAX arrays. And next is the dispatcher hook. There is this API called Torch Dispatch. This is the API provided by PyTorch themselves to pass the information, do a callback every time some PyTorch ops are running on top of a PyTorch tensor. So we register that hook, and we will get a callback here. So for example, if I have two tensors, A and B, and I call torch.add, you will call torch dispatch, which is a hook we registered, and it will tell us, hey, the operator right now is A10 add, and the two inputs here are the Python references of the tensor A and the tensor B, right? From those two subclasses, we can get the JAX array inside of it, because we know inside of it is a JAX array. And then with this op name, we can do the lookup in our dictionary. We get a JAX function, which implements torch.add. We call it. We get a JAX array in return. We wrap it again into our tensor subclass. XLA tensor used to be the name. Now it's called Torchax.tensor, but those are, I didn't update the slides. Sorry about that. But here, the beauty is this. PyTorch doesn't know what is inside of your subclass, and it doesn't care what's inside of your subclass. And that's kind of like the whole point of subclassing and OOP is that implementation details are implementation details, right? And how JAX-JIT works is that when you JAX-JIT, inside of my tensor will not be jmp.nd array. It will be this JAX.traced object, which is what JAX used to trace your graph. And this tracer object will also flow into Torch dispatch. We will do our dictionary lookup. We will call the JAX functions and we'll wrap it up again. But the JAX tracer will not remember that there's a dictionary lookup, there's some Torch dispatch magic. You will only remember JAX operators which have been run on top. So you will record jmp.add. You will discard all of the other Python stuff that it doesn't care. So after that, we can get a clean JAX graph out of it. So even if I put like instead of jmp.nd array, if I put torch tensor, TF tensor for TensorFlow, it will work the same way as long as we have the implementations for every core PyTorch ops. Right. So after that together, then what we have done so far is that we have implementation of PyTorch ops in terms of JAX. Kind of like we only did the one-way mapping, right? Like how do you get a two-way interop? And here's a kind of like also a little bit of magic is that this tensor that wraps the JMP array, we can have two functions. I name them T to J, J to T, doesn't matter. But it's very obvious that those two are two functions. Like if you take a JAX array, you wrap it into tensor, and then you unwrap it, you get the same JAX array back, right? That's kind of obvious. And the tensor the same way. If you get the JAX array out of it, you wrap it with a, again, you will get a tensor with different IDs actually, but the same values inside. So turns out if you have two functions which you compose each other and they become identity, that's called isomorphism. And then if there's two spaces of objects, here my space are tensors and JAX arrays, and you have isomorphism between those two, it implies those two sets are identical, are the same thing from the mathematical standpoints. So here we have isomorphism between two set of tensors and arrays. What about the models, right? Because what we care is to run models. And it turns out if you have isomorphism of spaces, you have isomorphism of functions. So given any function that takes torch tensor as input and returns torch tensor as output, we can construct this function g by doing this composition t to j dot f dot t to j, basically wrapping the unwrapping the torch tensors and get the JAX arrays, call the JAX function, and rewrapping again. And here we get a correspondence, which is also a isomorphism. So F to G mapping is isomorphism, G to F is also isomorphism. So we get isomorphism of functions. And that proves that the space of functions between set of PyTorch tensors and the space of function between set of JAX arrays are indistinguishable from a mathematical sense of view. And this is a guarantee that I can say, okay, any JAX feature that's gonna have today or in the future, it's gonna work. Right? So VMAP, JAX.grad for gradient computation. When TPU comes out with new ways to run JAX, could be pathways, could be sparse core support for JAX. All of those we get it for free, right? We can just wrap the functions and call the JAX API as is, and then unwrap it so that they become a torch tensor. Any questions so far? Okay, and what can we do with this? So basically, we can do two things, right? We can give JAX users the PyTorch ecosystem, right? Hugging Face just dropped support for Flux models, right? That happens last week. And guess what? You can put the PyTorch model through Torchax, and you get a JAX model out of it, right? You get two things in return. One is the PyTree of the weights as the JAX arrays, and one is a callable, which we just map them isomorphically, and then you can use with your JAX programs, right? You can use a Torch model, part of Torch model for maybe to encode your weights, to encode your input at some hidden layer, and then use that to train some JAX function, right? You can run Pallas, of course, because everything JAX arrays takes Pallas. You can call Pallas in JAX arrays. And then here, in case of vLLM, what we're using, what we're leveraging Torchax is we can use the same code to support both. Because after you map it, the JAX function that you mapped from Torch function is as good as any from the coding perspective. It doesn't see that it's different, right? And of course, I'm very curious of what people can, why are there any other reasons why people want to write PyTorch and JAX in the same program or use them together, right? So, and here's a little bit picture of what vLLM will take advantage of this. So vLLM worker need to call the model, right? And when you call the model, it either need to pass torch sensors down or need to pass JAX array down. Doesn't matter. So in the beginning, if a model is released in PyTorch, you will have the PyTorch GPU model code. You can use Torchax to call it directly here, and it will be in this scenario, right? And as time goes by, or maybe you are optimizing, you say, oh, we already have this attention layer, or this that's already pre-optimized, and here it uses attention. Maybe I can swap out the module to another JAX module wrapped with the core JAX, and then from here, from the vLLM worker's perspective, it doesn't know that inside there's a core JAX. It just give it a bunch of tensors and get a bunch of tensor back. It flows nicely through here. And then as time goes by, you can even choose to replace the entire module with core JAX. So maybe everything is JAX. Or if you are a little bit lazier to say, okay, I'll replace the thing that I know is fast with core JAX, and I leave the few sub modules as torch modules with wrapped in core torch, right? Because as we can see, going back and forth between torch and JAX, you can go back and forth as many times as you want. It's not that you go to JAX and you cannot come back. You can call back as well, right? So one example that I like to give is, for example, for some of the LLMs with the image inputs, maybe you don't want to rewrite the image encoder, right? And you can call torch and use the torch code for the image encoder, and then maybe you already have a version of the LLM part in MaxTest, which is already pretty performant. You can plug them in using this technique. Yeah, so the upshot is that we have a library and which allows JAX and PyTorch to work together. And in the end, I really hope that in the future, the ecosystem boundary between JAX and PyTorch become muddier, and then there's really one ecosystem of machine learning instead of JAX ecosystem bubble and Torch ecosystem bubble. And then the people who's writing these frameworks just choose the UX they like most, right? If you like functional programming, maybe you want to write JAX. If you like OOP, maybe you want to write PyTorch. But it doesn't matter, right? You still get access to the entire ecosystem. That will be a future that we can bring in the future.
What's the advantage it has over using Torchax?
So Torchax cannot do core JAX. Well, it actually can, as we added in this release, but actually also use Torchax, right? So now we're not positioning like Torchax and Torchax. They're the same library. It's just pieces of the same library. Users do not need to modify their code. Users do not need to modify. But yes, some feature will go through Torchax, especially if you want to interact with JAX, right? If you say, oh, I just want my model to run on TPU, so one story. If you say, oh, I want to write some code which works with both JAX and Torch, and the same code path, right? That's when the Torchax component shines.
Is it also JAX primitives though that it uses under the hood, so it'll lower using JAX primitives?
Yeah.
So that's the core difference between PyTorch XLA and Torchax as well. Yeah.
Right.
Any other
yes.
questions?
How is the sharding annotation and collectives?
Yeah, a very good question. How is the sharding annotation collectives handled? And the short answer is whatever JAX does, we do it the same way. So a little bit longer answer is that yes. So the mesh, when we create a mesh, we are doing JAX.make mesh. You get a JAX mesh. You call JAX.lax with sharding constraint to mark shardings on Torchax tensors. We have done some helpers which you can say .shard and just give a sharding constraint as shorthand. But in the end, it will call JAX.lax with sharding constraint. So everything that works with JAX works here. And same applies for, I removed some of the slides. So if you want to do profiling, call JAX profiler. JAX.profile scope shows up in the profile. If you want to do like AOT or like a compilation cache, basically every feature that works in JAX work on Torchax without change. Questions? Yes.
So I understand you've been mostly focused on the compute side of things.
Yes.
But why do you believe this would not work in the RGPU backend because of the PCRG stuff? Like it's just going to be a different plugin. Everything else is
Correct. It will also work on GPU. So if you want to write PyTorch and JAX together in GPU using Torchax is totally a valid use case. Confession from my side, I haven't tried it, right? So Will it be fast? I don't know, because you usually in theory everything should work, but in practice I'm more reserved to say, if I say it wrong, I better try it myself, and I haven't tried it myself.
Okay, so LLM-d. Okay, so I'm going to zoom out a little bit. So inference use cases over the last year or so, or maybe 2 years, depending on where you work, have changed significantly. We are scaling compute very, very quickly now, largely because of different use case patterns. The first pattern here is maybe a more traditional pattern where you would be more prefill heavy. And when I say prefill, it's just the number of tokens that are passed all at once at the beginning, and then decode would be auto-regressively generating tokens one by one. So traditional patterns would have been very prefill heavy, where let's say I'm taking this very long document and I have to summarize it down to a very short snippet. If I go to now reasoning models, so actually the first pattern is actually very compute bound, depending on how prefill heavy you are. So the stress on the system is very different than the second pattern, where it flips this completely on its head, where you're decoding significantly more tokens than you're actually prefilling. And so now you're memory bound, right? The same model, just completely different stress that you're putting on the system from a different request. Then you go into agentic patterns, where now models can call tools, and it might call a tool and it might take an hour, right, before the tool is actually done processing something and then come back to that. And so now you have a state, and if you don't handle that effectively, you're basically idle for an hour waiting for some response to come back. And so there's multiple passes. There might be some undetermined amount of time between those passes, and you have to manage state between those passes as well. So this is all very, very complicated. And so things like disaggregated serving have kind of become popularized in the last 6 months or so, where you can handle these two very distinct patterns quite differently and scale nodes based on what requests look like, based on the demand of your system. I could go into load balancers or whatnot. So traditional load balancing, microservices, when you think of it, is very cheap, very simplistic, and uniform, right? But as you start to try and use the same load balancers for large language model serving, you start to see like how the patterns that I had just discussed previously start getting very, very complex. And routing becomes really important, right? Routing and then state managements of state. So it's very slow, it's not uniform, and the underlying compute, as you all know, is very expensive. And so that's what LLM-d is trying to solve, right? So it's a Kubernetes native set of optimizations that the orchestrator really handles, but it works really, really well with vLLM as an engine, as the backbone engine. And so the types of things that are landing in LLM-d that you'll have available on TPU and GPU are things like hierarchical KV cache for state management, like I had mentioned previously, but also disaggregated serving for keeping latency really, really low and being able to handle very different request patterns or data distribution patterns, like I had mentioned. And then what else is there that I can't really? Hierarchical, disag, smart routing. Maybe it'll come back to me. If it comes back to me, I'll come back to it. And so significant case, so you can actually have bottlenecks at the server level, but your bottlenecks are actually above your system, right? So it's a full system stack that needs to be optimized. And so to use LLM-d, you're not just looking at the server. There's a repo. I can actually just share it here. LLM-d, it's basically how would you package a bunch of really neat open source tooling together so that it works really, really well in an end-to-end way, depending on what use case you have. And so if you need disaggregated serving, it plugs in with vLLM and then orchestrates disaggregated serving, so scales your prefill nodes and your decode nodes. And the reason why LLM-d was really released is because there was nothing really like that. Actually, Dynamo came out, NVIDIA announced it a few months ago, but there was really nothing like it in the open source ecosystem. Every single lab had to create their own. And so now there's an opinionated way of doing this in the open source, and it's hardware interoperable, so it works with GPUs and TPUs. So JAX support announcement. If you go to these repos, you won't see anything about JAX yet. That's because this is the first talk that we've given publicly about it. So, but stay tuned, and it's coming. So thanks very much.
What is that? So it seems like you guys are pursuing vLLM for inference, but Jetstream also exists?
Jetstream also exists, and actually the disaggregated functionality of Jetstream is actually what we're using in the JAX backend for vLLM.
So how should I think about like using vLLM versus JAX if I'm running on Jetstream if I'm running on TPUs? Like
you can use both. So it's really just you can use either or.
like what use cases is one better for the other?
Well, right now we don't support JAX at all in vLLM, and so that's how you can think of it right now. And then by
to get rid of Jetstream and move to vLLM completely, or?
No, not. I think we're like thinking of ways to consolidate both so that we have great like the functionality that you have in Jetstream is also available in vLLM with the JAX backend. Yeah. Any other questions? Yeah.
So I guess go back to my previous question just to help me more understand. So you also have a JAX implementation of different models.
Yes. Let me go back to that slide just to. Yes. So we have JAX. What it's written in doesn't matter. If we just think like the reason we would rewrite a model implementation is to get the best performance on TPU. And so like forget about JAX, PyTorch, Torchax, whatever. We will use whatever is available so that you get the best performance for that particular model. And it just so happens that the way you would write a model implementation performantly with GPU is going to be slightly different than how you would write it on TPU. And we want to capture those optimizations. So it will, I don't want to say like it will be all JAX or it will be whatever is the most performant. No, Torchax. So so this is important. So day zero really important. Optimal perform like I just explained, the GPU implementation is not going to be as performant as the TPU implementation. And so while we're writing the most performant TPU implementation, we want you to have access to a model on day zero, right? And so when a PyTorch model that was probably written by someone thinking about TPU somewhere out in the world, when that lands on day zero in vLLM, we want you to be able to use it on TPU. And that will use Torchax and it will read Torch, but it will lower using JAX primitives, but you won't really, that'll be totally abstracted from you. But then as soon as we can, especially if it's a really popular model that gets used a lot, we want to rewrite as the parts that we can so that they run as performantly as possible on TPU, and that will be with JAX.
And if I'm not wrong, I think you can still run on TPU using Torchax.
Today it uses Torch XLA. So if we kept on the path of Torch XLA, we would have two separate code paths. Super inefficient, right? We'd have to maintain two separate code paths, whereas with Torchax, we can actually unify the backends with JAX and Torch using a bit of glue and I'm actually going to bring up your slide because I think it's really important too. This slide kind of talks about the process of going from one end to the other. Han, I don't know if you want to.
Right. So just to be very clear, when running a PyTorch module under Torchax, you are essentially running JAX, except the JAX is hidden. It's like this will call some Python functions, will call some other Python functions, will call some other Python function. Eventually, you will call JMP numpy ops or JAX or lax ops. It will eventually you all get to JAX ops, right? So the moment you run the PyTorch module on Torchax, technically you are already using JAX. The same way that technically if you use Flax and don't use JMP directly, you are still using JAX, right? In that sense, but it's PyTorch, right? So and then the issue is that can we have a PyTorch model as performant as a JAX model? Yes, you also can. But I'll give you one example that if you optimize it for GPU, if you do stride manipulation, right? You get a stride out from a tensor, you do some math on it, you compute a new stride, a new size, and you say torch.sthreaded, here's my storage, here's my threads. On GPU, that's very fast. 0 copy, only modify metadata, nothing else, right? That's blazing fast on GPU. That's terrible on TPU. You don't get threads on TPU. Every thread is a scatter. You actually need to do index lookup, and it will be terrible, right? So even though it runs, if you do torch.xthreaded in Torchax, it will run. It will be terrible. And there's a few things you can do about it, right? We either say, oh, here this submodule is slow. Maybe I just rewrite that submodule. Do I just modify the torch code so that it becomes TPU-friendly torch, or do I swap with the JAX submodule? It depends on whoever's working on it. Could be that there's already a JAX submodule written, and then I just call it. Maybe inside of MacTest, or maybe inside of Flags or somewhere else, and I can just call it. Then maybe I prefer to call JAX and submodule, or maybe not. If I just need to change the in-place mutation to a functional version that returns a new value, maybe I want to do it in Torch. But the goal is, as Brittany hinted, is to get the best performance, right? And to say, when do I stop? Do I need to gradually move one module by module until the point where I have no PyTorch left and everything is JAX? If I choose to do so and it's convenient for performance, I will do it, but it's not a requirement. Basically, the flexibility is here for us to say, either we migrate gradually, we say piece by piece, and every piece you move, we can say, from here we got 5% performance, from there we get 10% more, right? Every piece we do, we get a little bit out of it, and we can decide when to stop, right? We can say, okay, maybe this is good enough for now, until somebody write a new something new that completely blows the performance, or maybe you say, oh, it's not enough. Let's keep going when everything until everything becomes JAX, and then we know for sure we can go further, right? So all valid possibilities. Yes. So right now, this is a TPU focus, yes, and the whole software thing should just work. But again, we need to try it and verify. Yeah. So if you have a JAX function, meaning a function that takes JAX arrays as input, right? And to call it, you just, if you want to call it with JAX arrays, you just call it normal. Yes, what you would do. If you want to call the same function but passing PyTorch tensors and have it to return PyTorch tensors, you will do call JAX, the function name, comma, and the args, right?
How is that useful? Is that useful for running PyTorch model on TPU?
It's useful to insert some JAX code inside of PyTorch code. So
the example you had with multimodal is really good. I think because a vision encoder, there's so many different variants of a vision encoder. For instance, that might be in the implementation might be in PyTorch or PyTorch, but you might have the LLM that's ready to go and fully optimized written in JAX. Like it might use a llama model or something. You could literally just call the already TPU optimized version of the LLM while still using the vision encoder that was written in PyTorch. It's really to support, like, we're not always definitive in what we want to do, right? Like sometimes just trying things out and seeing if it works for your use case is what you need to do leading up to this last end state where, it's as blazing fast as possible. And so we want to support people throughout that journey. And so the most critical models will be written in JAX, or the goal is really to just get the best performance possible on TPU while supporting a JAX backend. So all the composable parts like attention will be written in JAX. And so you can bring your own custom model like what Pengchong had discussed. But then on the flip side, there's also this whole other ecosystem within vLLM that we also want to support too, which is using PyTorch.
Yeah. So just to add a little bit more in color. So one advantage is that even if you want to migrate to JAX, right, fully migrate to JAX, gradual migration is better than one shot, right? If you can do piece by piece, and every of those pieces passes your unit test, you can merge the PR and have people getting benefit of it. You can keep doing that instead of hiding a cave, do 2 months of full rewrite, and then come back and maybe you had 50% of failure unit tests you have to fix back and all those experience, right? So that's one use case. And the second use case is that, like as a engineer, it's not always fun to rewrite a piece of math from PyTorch to JAX just to have it running, right? If you just have PyTorch by one side and JAX in the other side with no interop between, that means either your entire model is written in PyTorch or your entire model is written in JAX. Then you have to translate every single little math. And then when you get a numerical issue, you have to say, oh, did I translate the math wrong or what, right? with Torchax, you can say, okay, this piece I didn't change, I just wrap it. I don't have to check. This piece I didn't change, I just wrap it and don't have to check. These 3 lines I rewrite in JAX to call some Palace kernels, I only need to check the numeric there, right? So having a tool for gradual migration is always beneficial.
So we're at time and my next meeting has started, but that's fine. Yeah, thanks very much. If you have any questions, we can always chat after. Yeah, thanks so much for coming. Appreciate it.